Okay, so it's my pleasure to announce the first talk of this seminar by Nuria from Universitat de Barcelona. She will talk about quasiconformal surgery on moderate domains.
Okay, so good morning, everybody. Thank you for the unexpected opportunity to participate and to give this talk. So this is a talk about kind of a tool that we are using in a bigger framework than the one that I will speak about. So it's answering a very particular question that I will pose in a second. And then I will leave the big motivation or why this is interesting for us for the end, okay? So this is very important, joint work with Vasiliki Evdoridou, Leticia Pardo-Simon, now in Barcelona, Lukas, Geyer, University of Montana, Fatou from the Open University in the UK. So, well, the setup where we are going to be, maybe I can switch off the light, or is it possible? Or then when we use the blackboard, I will switch it on again. Okay? So we'll be in the usual setup of, well, in this case, we will be iterating entire functions. Since we are going to be talking about wandering domains, we need them to be transcendental, so non-polynomial entire functions, and they are iterates on the plane. And I don't need to explain here that we have this division into these two totally invariant sets, the Fatou set and the Julia set. Fatou set associated to stability, to normality, to equicontinuity, open set. The Julia set is like the boundary between these different behaviors, and therefore is where you see chaos, closure of set of repelling periodic points, everything that you can associate to the concept of chaos, right? And it's this boundary between the different stable components, so it supports all the tension in these regions. So the Fatou components can be, they are open, they are simply connected because we are in the entire setting, for now, at least for periodic components or pre-periodic, and their boundaries are in the Julia set, they map one to the other, so you have kind of a dynamical system of Fatou components. So you can take a Fatou component and it will necessarily be of one of these three types. It will either be periodic, it will come back to itself, or pre-periodic, eventually falling into a cycle of components, or wandering. So it could be that your Fatou component wanders forever in your complex plane, either marching off to infinity or accumulating in the plane, but never intersecting any of the previous members of the orbit. So if you, let's start first with the periodic Fatou component. So if you have a Fatou component, a stable component, simply connected, this is a very nice boundary, but it could be awful, no? It could be like totally locally not connected, well, as awful as you want to imagine it, but simply connected domain. You can always map it under the Riemann map to the unit disk, a conformal Riemann map, as you know, and well, you can build this diagram so you can define a map on the unit disk which reflects the dynamics of F inside your component. And this is what's called an inner function. You can prove that it's an inner function, meaning that it is a holomorphic map of the disk with radial limits almost everywhere. Okay, belonging to the boundary of the disk. And big warning is that this diagram that looks so nice and so innocent, you could have non-extension to the boundary here and non-extension to the boundary here. So it's absolutely non-trivial to deduce things about the dynamics on the boundary of neither the two, no? But we are not going to care much about this today. What's important is that in the interior we do have a nice holomorphic conjugacy. Conformal conjugacy. So transferring results from G to F, at least on the boundary, it's not always possible, but in the interior it is. And let me just remind you that if the degree happens to be finite, then the bottom is simply a Blaschke product, which we all know and love and understand. Okay? So for when this is not a Blaschke product, or well, in general actually, we have this Denjoy-Wolf theorem that tells you that any holomorphic map of the disk has very simple dynamics inside. It either all orbits converge to a point or all orbits converge to a point on the boundary. So that's all that it can happen. Or, it rotates around a fixed point in the middle. And those are the only three possibilities for a holomorphic map of the disk with no more conditions than those. And if you do that, and if you do some extra work to figure out how to move around this diagram, this gives you a complete classification of possible Fatou components, right? So the first case would be when the Fatou component is a basin of attraction, so you have a periodic fixed point inside and everything converges there. The second case could be either a parabolic basin, so you have a point of derivative 1 in the boundary and all orbits converge there, or a Baker domain, where all orbits converge to the boundary, but this boundary happens to be infinity, the essential singularity. Okay, so this is the second case in the Denjoy-Wolf theorem, and the third case would be the zero disks. Right? So you have a fixed point and everything rotates around it like an irrational rotation. Okay, so we know basically everything about periodic Fatou components, but you could ask about, I mean, we are not going to talk about this, but it's a very related question. You could say, well, so depending on my function or my Fatou component, I have one or another inner function, and you could ask which inner functions can be realized by a holomorphic, an entire map, and a given Fatou component. And this is a very fair question. And well, in the 80s, we had some very interesting particular examples, like for example, if this is the basin of attraction of an exponential with an off-full boundary, it turns out that this inner function is computable, e to the z plus 1 over z minus 1 or something like this, right? So this can sometimes be computed. We have examples by Baker, by Devani and Goldberg in the direction that I just said. But there is a little bit of a more systematic study in some recent work of Vaso, Lasserempe, and Dave Sixsmith called Fatou's Associates, right? And it's a very interesting paper where they explore this question of when this can be realized or not. Can I prescribe an inner function and build a function f that realizes? Okay. So this was for periodic components. Let's now go to wandering domains. So imagine that you have a Fatou component that just wanders around. This is an easy example, z plus 2 pi plus sine. So this blue point maps one to the other, and every other orbit successively gets closer and closer to this blue point, for example. And this goes marching off to infinity. Basically, so if you remove the 2 pi, they are all super attracting basins, okay? So all of these are fixed under z plus sine of z, right? This is a super attracting fixed point, so if you add 2 pi, since this is an almost periodic function, you get this wandering domain. This is a dirty trick to build trivial wandering domains, okay? So, a wandering domain its orbit never intersects its previous images, as I said. They only exist for transcendental maps. Nobody knew about them before the 80s. Baker was the first one to construct a wandering domain. It's not easy to construct examples except using these tricks that I just mentioned, because they are not associated to any periodic orbit. So there is no algebraic way to actually build functions with wandering domains unless you do what I just did before. So, you know, they may exist or not, but it's not easy to locate them or to find them or to know if a map has wandering domains or not. Not only they don't exist for rational maps, they don't exist for large classes of entire maps, because you need infinitely many singularities of the inverse. So, for example, infinitely many critical values, no? Zeros or images of zeros of the derivative, or infinitely many asymptotic values, like zeros of the zero for the exponential. So there are big classes without wandering domains, but nowadays major open questions are related to wandering domains. So They are very uncharted and there are still many questions about them, and in fact, I would say one of the big questions in the field is about wandering domains, whether bounded wandering domains with a bounded orbit exist. So, in order to address these questions, the first thing you need to do is to understand these objects. And as I said, they are not that well understood, so you need to understand them inside. And this is this project we have with Phil Rippon, Luis Stallard, Anna Benini, and Vasiliki Evdoridou, classification of internal dynamics of wandering domains. You also want to understand them in their boundary. So we also have like two follow-ups on what is going on or what can go on the boundary of these domains. And you also need to understand what is their relation with the singular values. Why do you need infinitely many values? Where can they be located on the plane? So it's like internal, boundary, and the relation with the exterior. And this is something that we worked in 2017 with Krzysztof Baranski and Bogusza Karpinska and Czarniecharke. And as far as I know, it's still the best result out there on the relation with singularities of the inverse, because this is not an easy problem. In fact, it's a very interesting question to really find out more about this relation, okay? I also would say it's one of the open problems that are worth looking at. Okay, so again, is this related to inner functions? No? And yes, it is. So you could take a base point arbitrarily, right? So z0, it's z max, z1, zn. Now these ones are already unbounded because I repeat, this thing could be unbounded with many. And I choose different now, of course, Riemann maps that map these zns to 0. So you are left on the bottom with a sequence, a composition of inner functions. So these are not associated to one inner function, but a wandering orbit is associated to a sequence of maps, holomorphic maps on the unit disk. And this is what's called a forward composition. It's in the realm of random dynamics, but without randomness. So it's like a given sequence. And of course, it's not unique. Okay, so well, we say that, so this is a sequence of inner functions, we say it's associated, and in fact we say it's conformally equivalent, no? Because all these maps are conformal, and as I said, it's not unique, because I could choose another orbit, and interesting questions come of what happens if I choose a different orbit, do the properties of my sequence below change or not, or what happens, right? We will not get into this today. So I can repeat what I did for periodic ones, no? And I can ask myself, can every sequence of inner functions that I give you be realized by an actual true wandering orbit of an entire map, right? So the question is totally analogous, and also, if you can, what kind of function can realize it, depending on the properties or whatever. So the answer that we give to this problem is yes, under some conditions, okay? Which does not mean yes and only yes under some conditions, it just means that we can prove it under some conditions. And I think this is like the first example, and it could be much better, I think. So the theorem that I want to prove today, or give you an idea on how to prove it, is the following. If my sequence of inner functions is uniformly hyperbolic finite, a sequence of uniformly hyperbolic finite Blaschke products. So I am asking that the degree is finite, and I'm asking about the property that I will talk in the next slide, uniform hyperbolicity, then it can be realized. So if I do this condition, then we can build an entire transcendental function with an orbit of simply connected wandering domains and a sequence of conformal maps that make the diagram commute.
I'm sorry, you assume the degrees to be bounded?
Yes, and now I'm going to define this. Okay, so what do I mean by uniform hyperbolicity? I mean a sequence of finite Blaschke products, and now I will put a list of equivalent things that define this, no? So the first thing I want is that the degree is uniformly bounded, okay? We don't know how to do it if the degrees go to infinity. And this uniform hyperbolicity relates to having all zeros in a given disk inside, uniform for the whole sequence. So there needs to be a radius such that the zeros of each of them is inside this radius, and this is equivalent to ask that all critical points are in some other uniform disk for the whole sequence. And this is equivalent to asking, and this is a nice way to put it because this can lift to the wandering domain. So this is equivalent to ask, for example, that at least for one orbit, and if it happens for one, it happens for all, so that at least for one orbit, you have a constant such that this orbit is always at a bounded distance from the critical points of the
Hyperbolic distance.
The hyperbolic distance in the disk is always bounded from the critical points of the map, okay, which kind of tells you that they could be going to the boundary, but they have to be close to each other, right? And if it happens in one orbit, it happens in all. But anyway, at the level of the Blaschke product, so this is useful when you want to look at stairs, but when you look at the level of the Blaschke products, basically tells you that this sequence is not getting more and more degenerate with the critical points accumulating on the boundary or going to the boundary, okay? So it's a strong condition, but well, this is the condition that we need in order to make our surgery work. Maybe you can do it in more relaxed conditions, I'm kind of sure that you could. Okay, in any of these cases, we say that this sequence is uniformly hyperbolic, okay? So observe that if you have this, and in fact what we are going to use we have colors, that's great. So what we are going to use, for now let me just put it here, is that, okay, here. Let's not waste the parts that we will need. So if this is my sequence of disks, this says that if I fix the disk of radius r in all of them, that contains all the zeros and all the critical points, take the maximum between r and s, and then the preimage of this disk under this map, Bn, will be something surrounding the disk R, okay? And the same here, right? And the same here. So basically everything interesting will be happening here, and my map will be basically a covering on anything else, okay? So all the critical points are inside, and any orbit in the dr will remain in dr forever. This is super important to realize, and in fact, any orbit in this annulus, at the next teacher it will fall inside the R, and therefore it will remain in the R forever. So this is a consequence, and this is the key consequence that we are asking, the key property that we will be using. Okay, so we will prove that this function exists using a surgery construction, right? And this is good because we will have control on the final function. So in our applications, which as I said, I will explain at the end, this is essential. We want to know which kind of function we obtained at the end that realizes the map, that realizes the sequence, because I just want to say that there is other ways to do this. And in fact, you get more general results. So recently, Vaso, David Martipete, and Lasserre have announced that they can actually prove this theorem in much more general conditions, but they use approximation theory. And with approximation theory, yes, you have a realization theorem, but you have no idea which kind of function you get at the end. It's like an approximation of maps. So it could have infinitely many singular values, you don't know where they are, you don't know the order of growth. So you have less control, but you get a more general result. So we will use surgery And before I go into the proof, I want to observe to you that doing surgery only to modify a finite number of steps is really simple somehow, and it has been done before, in fact. So when with Christian Hendriksen, we were looking at precisely this motivation type Muller space of wandering domains, we already performed some little modifications by surgery, but only on a finite number of steps. In this paper I mentioned before, where they look at the possible realization of inner functions, they also use this. So let me show you in the blackboard in a moment that doing surgery on a finite number of steps always works basically no matter what you do. And now I need to ask you, I prepared 3 slides about what it is about doing quasi-conformal surgery. I don't know if I can skip them, go fast over them. What is it that, so I know this is the type of question that you don't want to be asked in a talk, but I ask you, is it worth it that I go through these 3 slides and I go like
Don't skip it.
Don't skip it. Don't skip it. Good. Perfect.
I'm going slowly.
Okay, fine. No, that's why I prepared them, right? Because I was not sure if this would...
The end of the talk.
So, unfortunately, this is not, it's a crash course in 3 slides, okay? This could take it should take longer, but maybe it gives an idea of what we are doing later. So, quasi-conformality is just a degree of regularity, right? And a quasi-conformal map from a set to another open set, it's simply a homeomorphism that is orientation preserving and it has some properties. Basically, it says that angles are deformed in a bounded fashion, so that you don't preserve angles like conformal maps, but you modify them only in a bounded way. So in formula, this tells you that, so by the way, they are differentiable almost everywhere, not necessarily differentiable. And what this tells you is that when you look at this is the quantity, the derivative with respect to z bar over the derivative of z. So if the derivative with respect to z bar is 0, this is conformal. If it's not 0, this quantity measures how far you are from being conformal, somehow. And what you are asking here is that you are a bounded distance away from being conformal. Okay, so that the supremum, the infinite norm of this thing, wherever it's defined, because remember we only have differentiability almost everywhere, is bounded away from 1. So you want it to be as near, the closer to 0 it is, the closer you are to being conformal. Okay, so being this big K is this one will go from 1 to infinity, this one will go from 0 to 1. So if you are 1 quasi-conformal, you are 0 here, so you are conformal. And this is what it measures, the distortion on angles that you can be having. Okay? And this mu basically encodes the information of what the differential does at that point. So the differential from one point in the tangent space to its image sends circles to circles if I am conformal, and circles to ellipses if I am quasi-conformal. And this is measuring the eccentricity of these ellipses. Okay, so this is the formal definition of quasi-conformality. Why are we interested in this type of maps? Because, when you want to build models, building models of holomorphic maps are super rigid, right? And if I define one holomorphic map here and one here, the chance that they paste into a globally holomorphic map is 0, right? Instead, curiously, if I do it with quasi-conformal or quasi-regular, which is basically the same, if I paste them, two quasi-conformal maps pasted along a reasonable curve are still quasi-conformal. So this is really the power of it, that it allows you to build maps with a lot of flexibility. Remember that composing multiplies the distortion. Remember that going back or going forward or backward is basically the same type of distortion. And we are going to be talking about quasi-regular maps because we are going to allow critical points. So just for you to have an idea, conformal is to holomorphic exactly as quasi-conformal is to quasi-regular. So a holomorphic map is locally conformal except for a discrete set of points. A quasi-regular map is locally quasi-conformal except at a discrete set of points. Okay, so quasi-regular maps are these ones that we build as models. So when we want to find an example of something, we leave the holomorphic world, so we enlarge, we find a quasi-regular map that does dynamically what we want, and we hope that we will be able to come back to the holomorphic world, finding like a copy, a conjugate copy. So we will want at the end to go back to a holomorphic function which is conjugate to the model that we built. Okay? And this is what one does when performs surgery. Okay? Basically, you construct your map a little more flexible, quasi-regular, and then you hope that you can actually find a holomorphic map that does what you designed. This is what you are doing. So, how to know when I can come back? So here I went with my scissors, with my needle, and I built my quasi-regular map that does exactly what I want, and now the question is this really a holomorphic map? No? So can I really find one that is a copy? So the sharpest answer to this, and this is the only one we are going to use today, although it's not, well, it's the one that I will use, is simply that you can go back as long as all iterates are uniformly k quasi-regular. What does that mean? It means that if my map is k quasi-conformal or k quasi-regular, when I do g squared, it's also with the same k, and g cubed and g to the 4. In other words, my orbits don't go through k quasi-conformal regions infinitely many times. Okay, so this multiplication that I get from composition, when I look at one orbit particularly, does not apply, because my composition only has a finite number of terms where I am actually applying a QC map. So in my pasting in the regions, I have to do it smartly so that orbits don't go through the bad regions infinitely often. Okay? As long as this is true, I know that I will have a conjugacy to some holomorphic map. And conjugacy is the magic word because conjugate things have the same dynamics. So if my model had the dynamics I want, my holomorphic conjugate will also have the dynamics I want. Okay? This is the philosophy. This is how to, just to say that this is proven, or let's say, what really makes this work is the very well known the measurable Riemann mapping theorem or integrability theorem, right? And this is due to Mori, Alfors, Beers, Boyarsky. This is a big subject with many different conditions, etc. And it just says that if you build a measurable function, it's really finding a solution of this PDE. Okay, this is what's called the Beltrami equation, and it just says, give me a measurable function here, and then I will find you a phi that satisfies this equation. So it's like integrating your derivatives. Okay, we are not going to use this much, we are just going to do a qualitative construction. So let's see how to modify. So let me say how would you modify one of the inner functions. So imagine this is your UN. So this is my f, un plus 1, etc. So this is conjugate by my Riemann map to some dynamics on the disk, some bn plus 1 b. And imagine that I don't want to have a holomorphic conjugacy to Bn, but I want to have a holomorphic conjugacy, a conformal conjugacy to Bn tilde, but only this one, right? I just want to convince you that doing surgery here is really simple, because philosophically, right? Forget about all this. Philosophically, in total generality, I could simply replace my function on UN by whatever I want. So, for example, I could define the function g, which is f outside of my wandering domain UN, right? And some f tilde on UN in such a way that they glue continuously, and in such a way that f tilde is whatever, k quasi-regular. So it could have critical points or whatever, but it has just one distortion constant k. Whatever, I don't care, right? And what would be the resulting map G doing? Look at orbits, right? Because this is a wandering domain, I will never return. So take a random orbit. Either it will never enter in UN, and therefore it will be holomorphic forever, right? Or if it happens to enter here, it will enter, leave, and never come back, right? So G, no matter what I put in there, right, is Gm is uniformly k equals 0. And then Sullivan's theorem tells me, then great. This means that you'll have a conjugacy, right? A quasi-conformal conjugacy to some other function, big G. So G will be quasi-conformally conjugate to some big G holomorphic. So I know that I will be able to conjugate to something. Because it's conjugate, it will still have my wandering domain, etc., etc. Now here I told you to put whatever. If you just want it to be holomorphic, so now the part is, what do I put here so that really at the end I have a conformal conjugacy in this step to my Bn tilde. Okay, so it's like I can put whatever. So I'm sure you believe me that I could arrange this diagram. In fact, what I have to do is to put here some quasi-conformal map at the level of the disk that makes this diagram commute, and then in here glue this Bn tilde. So I go down by a quasi-conformal map, I do Bn tilde, and I come back. Well, if you do this gluing in a little bit of a smart way, you will end up having, at the end of the day, you've just modified one step of the inner function that is associated. Okay? But the philosophy that I want to transmit here is wandering domains are great to do surgery as long as you only do it in a finite number of steps. You can basically do whatever you want as long as it matches continuously on the boundary and it does what. Because they have this property that orbits never come back to them. Okay? So why is this, what is the difficulty of what I'm doing is like the question, recall, this is the same slide we had before. What we want to prove is that you can do this infinitely many times at once. Okay, that is the difficulty, because if you change this in all the UNs, right, then your orbit will go through bad regions infinitely many times, right? So you have to, that is the difficulty of what we are doing, that we really want to realize a whole sequence of inner functions on the bottom, not only a finite number, okay? Okay, so how does one do this? And here I will not give many details, but I will give you an idea, and I'm sure that after understanding this will not be so cryptic. So what I want to do here is to do this infinitely many times at once. So I have to fight two problems, and that's why we need this uniform hyperbolicity, right? So the first thing, do you see over there? Yes? Okay, so let's do it here. So here's my UN minus 1, UN plus 1, etc. that's my F, right? Here is my original Blaschke sequence. And here is the one I would actually like to see after I'm done. Okay, so let's do exactly as we did there. And let's just, well, let me draw something else, because remember we have this uniform hyperbolicity. So this means that if I take the minimum R between here and here, right, I can draw this disk of radius R, same disk everywhere, right? And I know that the pre-image of this disk will be at all levels some kind of, right, something that will, so this goes to the blue, so every orange goes to the next blue. Okay, I can actually translate this on the top, so here it is not going to be a disk, but I can lift by a conformal map, so here I will have some core part, right, and then I will have some curve here, and remember, all critical points are going to be inside this blue region, huh? Okay, so just forget about this for a moment, and let me tell you what we are going to do. So what we are going to do at this level, and this is the easy one to understand, is to change my map only on the blue part. So I'm going to define a new function, exactly as I did before. So my G will be F, clearly F, here I will not be very precise mathematically, but I hope that this will be enough. F on the complement of the union of the wandering domains, that's obvious, right? I don't want to modify anything anywhere else except inside the wandering domains. Now I'm going to define phi n minus 1 identity phi n, well, let me do it at this level. Phi n identity, so bn tilde phi n minus 1 plus 1, sorry, and inverse, so I'm in the blue region. So this is really where I'm doing the replacement. So I go by a conformal map, this is the identity because it's the same disk, and now I glue my new map inside here, but notice that this is conformal. Okay, not conformal, sorry, it's holomorphic. Okay, because this is the Riemann map, this is a Blaschke product, and this is the Riemann map. So in my blue region, I've modified my map essentially, because here is where actually the important things are happening, and I'm doing it holomorphically. Now, I'm going to leave F as it is on the outer annulus, which I'm going to call, I don't know, Bn minus 1, Bn, etc. So F on my outer annulus, okay? And now what am I going to do in the middle part? I'm going to interpolate. So on the middle, I'm going to define, I don't know how to call it, psi n, if you want. I'm interpolating between the two ones, between what I've done inside and what I've done here, which has the same degree, by the way. Of course, it would be a problem. So this part is the one that is going to be Kn quasi-conformal. Okay? This is the only part that is really going to give you a quasi-regular. It's going to be holomorphic here. I have changed nothing out there, and in this small annulus, right, in these ANs, let me say, so this is AN, this is AN minus 1. In here is where the map fails to be holomorphic. And now it's easy easy to understand why this is gonna work. First, well, I need to prove something that is really the core proof, which is Kn equals K, or less or equal than a certain K for all n. This is the technical part. So I need to prove that, which I will want proof here, that I can do this uniformly on n. Okay, why? You'll see, well, but still, it's easy to understand why this is gonna work, because now I take a random orbit. Again, if it never falls in my wandering domains, I don't worry. But if it falls, where can it fall? It can fall in the outer annulus. So if it falls in the outer annulus, my next is holomorphic. If eventually, which it will, falls into the small annulus, and the next, it's in the blue part, which is holomorphic. So it can only step on the annulus, on the bad annuli, once. Okay? So this tells you that at least the iterates, so if this is true, the iterates will be uniformly K, quasi-regular. Now, it's important to know that the K here is the same as the K here, it's the same as the K here, because if not, even G itself, without iterates, would not be K quasi-regular, right? So if this has distortion 10, 20 million, this will not work. Okay, so this is really the idea of what we will do, or what I claim that we do, except that as it happened before, one needs to do it a little to get all these estimates. The real work is done at the level of the disk, and we will not get into these details, but because I think what I just explained is enough in order to at least understand what kind of things we're doing. Because this gluing, this interpolating, you actually build it here. So you actually build some quasiconformal maps here, right? Which quasiconformal maps uniformly quasiconformal that make this diagram commute in the whole. They are the identity on the blue disk and some kind of combination in the rest, and you use this function to really glue Bn tilde inside. But this is irrelevant, I think, in the big picture. And what I am skipping, well, this exactly as it happened there, because this is uniformly quasi-regular, I would be able to integrate, again, obtaining some kind of, so we've killed this level somehow, and we would obtain a map up there, big G, which is holomorphic, which is quasi-conformally conjugate to my model that I built. And here is the part that I'm not getting into. Really, this combination is conformal. So going from here to here, you get a conformal map, so that this is the new Blaschke sequence associated to your wandering domain of the new function. Okay? But in order to see this conformality, you really need to work with the complex structures, and I think now it's not maybe the moment. Okay? Well,
do you understand well that disks, when you do straightening, become a sequence of not regular disks for candidate to be
sorry?
here.
Say it again. Up there.
Up there, because of straightening,
Yes?
you obtain domains which are not disks. And
Oh, there, definitely. These were not disks, and these are not disks.
already here.
Already here, this was the dynamical plane with some wandering domain. Okay, so here they are not disks, here they are not disks, but when you put here the standard complex structure and you lift it right here, you get these ellipses, which by the way they are only, and then you spread by the dynamics. So up here you again have the standard complex structure everywhere, and that's why this is conformal.
Domains are not
No. This, I mean, this is even here. They could be, you know, the basins of attraction of exponentials. I mean, I don't know.
No, my question is because you meet at the end to construct F.
Yes, I know. At the
So
end,
you
I
have now
want G.
something in sequence of
Ah, okay.
and
So
then you need to know
Good.
the outside.
good.
Maybe you have standard structure outside, and when you straighten it. Oh, that's what my question. How you cope with this outside?
how I cope with finding this initial
And
one,
finding F, what's the
little f or big G up here.
what was the initial F?
The initial f was at this level. I start with a map F with a wandering domain sequence. So
And then
No,
you want to
because
start with
then
abstract.
I replace, I start with this, which comes associated with this naturally, and then I prescribe a new sequence of Blaschke products, and I want to replace my sequence with something else.
But in F you have a priori.
F I have a
And you
priori,
want
and
to
I will mention now.
improve it.
Well, I want to know if I can find a function that realizes my Blaschke sequence. Yeah, now I understand what you mean. I start with a Blaschke
Yeah,
sequence,
you don't
with a
have
given.
any F.
I don't have anything. I will talk about the F now.
Yeah, that's what
And then I want to find a holomorphic map that realizes this one. And then the step one, and it's what we are going to talk now, is I need one to start with the degrees matching, right? So this is exactly what happens here. So how I find the template, how do I find my template where I glue where I replace my, so how do I find this level? Right? So I have this, and now I need this in order, and once I have this one, I can replace what I want. Okay, so, oops, no, so this, here. So I need to use, so either, if the degrees are all different, I don't have any other option than to actually go to approximation theory and find and construct an F which has wandering domains of exactly the degrees that I prescribe. However, if the degrees are all the same, then I have explicit formulas to find my original F. Okay?
Yes, answer.
And this is the one I would start with, and these are the domains where I would do the replacement. And that's how, at the end, I would find one which realizes my new Blaschke sequence and which I know perfectly what it does. And this is really what we needed because we had all degrees the same. So there are ways to find this template, and then the procedure is the one that inserts what you want inside the domains. And let me finish with some comments on the motivation of this, because I think that's also the interesting part. So why do I think this is interesting? Because as far as I know, a priori it's not so easy to think how to do surgery on infinitely many places at once where you just visit them all repeatedly, okay? So this is like one way that you can do this with total control. But why did we ever think about this? Is because our original work, or our paper, actually the subject that we are researching, is about deformations, quasi-conformal deformations of entire functions having wandering domains. So if your function does not have wandering domains, so it has only basins of attraction, parabolic, blah, 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 periodic Fatou components, then basically the framework of McMullen and Sullivan in '98 does it all. Okay, so it's well known how you can deform. Remember, deformation just means finding functions that are QC conjugate to your map, okay, and asking about the parameter space somehow, like how many dimensions you have, etc. So if you only have periodic components, it really, well, you need to work. So this is what we did here with Christian Henriksen, but basically the classification of McMullen-Sullivan goes through. So it doesn't matter if it's a basin of attraction of an entire map or if it's from a rational map. Of course, you have to deal with the infinite degree, you have to deal with some quasi-conformal isotopies, and it's not totally trivial, but you can manage, okay? And the results are basically similar. However, but to do this, so what we did with Christian actually was to look at Baker domains, which don't exist for rational maps, and we kind of gave a classification and we looked at how it can be, and then we just looked at some examples of wandering domains, and we started realizing that in the moment that you have a wandering domain, nothing is clear. So in this classification, it is important which type of Fatou component you are looking at. For example, it is important in the approach whether your grand orbit relation is discrete or it's not discrete. What does that mean? When you quotient by your map, so when you look at the grand orbit of a point, it may accumulate to each other or it may be discrete in your Fatou component. For example, if you are in a single disk, it's obviously indiscrete because it accumulates on an irrational curve, no? But instead, if you look in a basin of attraction, no, it is discrete because the images just accumulate on the boundary. So every Fatou component is in one category or another one. When you start looking at wandering domains, you find examples of wandering domains with indiscrete relations, examples of wandering domains with discrete relations, examples of wandering domains where you have no idea whether it's discrete or not. So suddenly you realize that this is a whole world, okay? And that if we want to understand parameter spaces of maps having wandering domains, even in the same component, which is exactly what we are doing, you really need to understand what's going on. So our motivation here was to start from zero by wondering whether the grand orbit relation was when would you have one type, the other type, so how could you classify wandering domains with respect to this? So in reality, our main result is to say that discrete and indiscrete grand orbit relations can coexist in the same wandering domain. So it's even that bad. So not only there are examples of every type, but in one same wandering sequence, you can have different pieces which behave completely different. In order to do this, what we did is to build such an example at the level of Blaschke sequences. So we built an example of a sequence of Blaschke products where this was happening, all of degree 2, simple, okay? And after doing that, we needed to be able to say that this actually happened in reality. And that's why this realization theorem was useful, right? To say, okay, we were able to build it here, now look, we can insert it into an actual dynamical plane with an actual wandering domain, okay? And if I have 1 minute more, I have like 5 minutes it seems, no? Okay, I can tell you this beautiful example at the level of the disk because it's one of my favorite things in the paper. Okay, so I will just give you a sketch. So which example will this be? So imagine that you take a polynomial, z squared plus epsilon, okay? Polynomial of degree 2. So q t of z equals z squared plus epsilon, something with a fixed point. Okay, well, if you prefer lambda z, well, whatever, you don't care, okay, with lambda small. So something with a fixed point that is attracting and only one component. Okay, so this polynomial has a basis of attraction of a fixed point. That's it. Right? Okay? And now take, so this polynomial has some equipotentials. So choose one, choose d0, and then its image will be an equipotential d1, an equipotential d2, etc. So this goes here with degree 2, this goes here with degree 2, etc. Now, dismember it. What does that mean? It means that I map d0, right? So take a Riemann map that maps d0 to a disk. So phi n going from dn to dn plus 1. To d, right? So here I will have my d0, which maps to a disk. Here I will have my d1, right, that maps to a disk by phi 1, etc. dn equipotential, which maps to a disk, right? Now my polynomial p maps d0 to d1. Here is my Julia set, which here will look smaller, right? And now my polynomial maps d1 to d2, and simply my Julia set will go to the Julia set, just that in this, well, actually it will look the same, sorry, these things grow, excuse me. So here this is the same, huh? Because this is bigger, this is bigger, this is bigger, this is enormous. But these ones are the same. So now I can define a sequence of Blaschke products, V0, which does phi 0 p phi 1, phi 1 p phi 2, etc. And here is where, at the beginning, I'll have a copy like this of the Julia set. Here it will be much smaller, right? Until it becomes basically super tiny. Yes? Okay, the magic here is that whatever it happens here inside the white and whatever it happens outside is totally independent in the same way that here these two parts are totally independent. And the magic is that what you see here that is expanding out, here it's contracting in. So this is uniformly hyperbolic very strongly. At the end, this is basically z squared, right? But still, orbits in here will behave, they will remember, they come from a basin of attraction, so 0 will go to 0, and everybody in the white region will converge to 0 like if it was in a basin of attraction. And everything outside here, if you check, and that maybe needs 3 minutes, okay, which I will invite you to take, is the orbit relation on the blue part is still remembering that it comes from a super attracting basin, so it's indiscrete. So notice that in here, if I take a point and I look at its grand orbit, its image is this, but its pre-image has 2 parts. No? And now the image of this is 1 point, its pre-image has 2 members, and now on this equipotential I have 4 members. All these points are in the same grand orbit. So actually the grand orbit of any point will accumulate in the whole equipotential. So it's really indiscrete. Instead, inside, orbits have a discrete grand orbit relation, right? So when you translate this here, you inherit this behavior. So in the same wandering domain, you have a whole region where the grand orbit relation will be indiscrete and a region where the orbit relation will be discrete. And this is example of Blaschke products of degree 2 showing this dichotomy, and by the procedure that I explained, you can glue it into an actual wandering domain and therefore get a wandering domain with this property. And that's it. Thank you very much for your attention. Questions or
Comments? Some questions were already answered, right?
yes?
Online questions. If not, then let's thank again.
Thank you.
And we have a break. Ah, we are perfectly on time.
That's true.
15 minutes
No.
break.
Break.
15 minutes break.
So is there a place?
Because next talk we have